Hello everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Welcome to today's lecture, Work Energy Theorem. So why it is important to engineering students, especially CSC students, what are the real world applications? So try to understand here foundation of physics and engineering. Energy is central to understanding motion, mechanics, and natural process. Natural process. So, trying to understand here, first one, you see here, foundation, physics, and engineering. So, you try to understand here what I am saying here, foundation of physics. Energy is one of the most basic ideas in science and also technology. So it is essential for understanding how things move, that is motion, how machine work, so how natural process happens. So in short, without energy, we cannot explain motion, technology, or even life process. So relevance to especially CSE students. Relevance to CSE. So we can think energy is only for mechanical or electrical engineers, but that is not true. It is important for all disciplines. So it is used in gaming and animation, gaming like Angry Birds or virtual or augmented reality, VR and AR reality. So use physics engines. These engines are based on energy concept to simulate realistic movements. Coming to this robotics related, robotics and artificial intelligence simulation. So robotics and AI systems need energy efficient motion planning so they can operate longer and smarter without wasting any power. So green computing. So optimizing the power uses in data centers. So data centers, servers and mobile devices consume a huge amount of power. Energy optimization is critical to reduce cost and environmental effects. What are the real world applications? So renewable energy technology, solar, wind, hydro, we can observe here. Energy's design systems to capture and use this solar, wind, and hydro related hydro energy, which are clean and sustainable sources. Coming to this electric vehicles. So electric vehicles and regenerative braking systems are real world applications of energy concepts, making transport more efficient and eco friendly related. So energy is not just a physics concept. What I am saying here, energy is not a just physics concept. It is the foundation that concepts physics, engineering, computer science, and real world technology. Whether you work on games, artificial intelligence, robotics, or sustainable systems, understanding energy will make you a better and more innovative engineer. So, coming to explain before work energy theorem, we need to understand what is work done. along the same direction and with the angle. So, what is the definition of work done? Whenever a force acting on a body displaces the body in the direction of the force, work is said to be by the product of the force and displacement of the body in the direction of force. So, let us take a body. The body is at rest. If you are supplying some force or applying some force on the body is moving along the one direction, same direction. Force and displacement direction is the same. At a displacement of s, then we get velocity v. So work done in general, you know very well, f bar dot s bar. So we can write this is fs cos theta in the same direction, in the same direction. Theta is equal to 0 degrees. Theta is equal to 0 degrees. So W is equal to Fs cos 0. So we can get F cos 0 is equal to 1. So the product of the force and displacement S of the body. So what is this work done? W is equal to F into S. Whenever a force is acting on a body, it displaces the body in the direction of force. Work is said to be done by the product of the force and displacement of the body in the direction of force. So that is W is equal to F into S. Case 2, case 1. If the force and the displacement of the body are in the same direction, so already we discussed in the same direction, this is Fs cos 0, that is equal to Fs. So coming to case 2, this is case 2. If the force F and the displacement S are in the different direction, the angle between F and S is theta, be the angle between them, the work done is given by W is equal to Fs cos theta. F dot S, that is Fs cos theta. The work done is equal to Fs cos theta, where W, the work done, is a scalar quantity. The SI system unit joule work done is independent of the path and time taken to do the work. So this is the work done. Again, you try to understand what is the definition. So the product of the force and displacement of the body in the direction of force is called work done. So if the force and the displacement of the body are in the same direction, the work done is given by W is equal to F dot S, that is equal to Fs cos 0. We get W is equal to Fs. If the force and displacement are in the different direction, the angle theta is the angle between F and displacement S, then the work done is equal to Fs cos theta. Fs cos theta. Work done is independent of the path and time taken to be the work. So that is a scalar quantity. The unit is joule. This is the work done. It is known as work done. What is energy? What is the definition of energy? The capacity to do work is called energy. So we can observe the energy in different forms. Kinetic energy, potential energy. The kinetic energy plus potential energy is known as total energy. It is also called mechanical energy. Mechanical energy. We can try to see here. The capacity to do work is called energy. So you see form of energies, kinetic energy. So due to the motion, we get kinetic energy, that is half mv square. Potential energy, due to the position or height, we will get the potential energy, that formula mgh. The kinetic energy plus potential energy is known as total energy, or it is also known as mechanical energy. Total energy or mechanical energy. Mechanical energy. So, different forms: heat energy, electrical energy, light energy, and so on. So, you can see this is the, you try to see this is the heat energy. Heat energy. You clear? You clearly understand. So this is also heat energy. Heat energy you try to observe. So the capacity to do work is called energy. Form of energy is kinetic energy, potential energy, heat energy, electrical energy, light energy, and so on. So the kinetic energy plus potential energy is called total energy. That is also known as mechanical energy. Mechanical energy. So you can see here, what is this? You try to observe clearly. This is the electrical energy. This is electrical energy. Electrical. It is also giving electrical energy, that is wind energy. So try to understand here both electric energy. These are the examples of electric energy. Electric energy. So coming to what about this light energy? Light energy. It is known as light energy. You try to understand clearly. So it is a torchlight. This is also light energy. Both are light energy related. You try to see clearly. Light energy. Both are giving the examples of light energy. So what is kinetic energy? The energy of motion is called kinetic energy. We know very well kinetic energy is equal to half mv square. Due to the motion, the object gets some displacement within particular time. So we can write this is s by t is equal to velocity. Due to the motion, it gets velocity. The energy of motion is called kinetic energy. Or another definition, you try to understand here, the energy possessed by a body by virtue of its motion is called kinetic energy. The energy possessed by a body by virtue of its motion is called kinetic energy. So, two definitions: the energy of motion is called kinetic energy, the energy possessed by a body by virtue of its motion is called kinetic energy. So kinetic energy formula half mv square, where m is the mass of the body, v is the velocity of the body. So coming to daily life examples. Moving a vehicle, if the vehicle is moving, it has some displacement. That displacement by time, it gives the velocity. If it has velocity, according to this formula, it gets kinetic energy. The energy of motion is called kinetic energy. The body has some velocity. It should have some energy. That energy is known as kinetic energy. So, flowing water, the flowing water is also having some velocity, some displacement. That's why. So, flowing water have the kinetic energy. So, flying bird also getting some velocity. So it has the kinetic energy. These are the daily life examples: moving vehicle, flowing water, flying bird, the aeroplane is moving. So any object is moving with velocity, it has some kinetic energy. So try to see the daily life examples here. The vehicle is moving. The vehicle is moving. So first of all, you try to observe the car is moving. After that, it has been changed as a scooty, two-wheeler. It is also moving. So both examples, both are vehicles. These are moving, getting displacement. Displacement by time, that is velocity. Due to this velocity, the vehicle has the kinetic energy. Kinetic energy. So coming to next example, flying bird. What is this? It is flying bird. So the flying bird is also having some kinetic energy. Due to the motion, it gets some kinetic energy. So water is flowing. What is this? Water, flowing water, flowing. The water is flowing. Flowing water gives some kinetic energy. So these are the examples you try to understand. Kinetic energy examples. Moving vehicle, moving vehicle. Three daily life examples we given here. You try to understand. So moving vehicle, number one, flowing water and flying bird. You clearly try to see here. Moving vehicle, flying bird, and flowing water. These are the kinetic energy examples. So expression for kinetic energy. Let us consider a body. At first, the body is at rest, so the initial velocity is equal to u is equal to 0. Let us consider a body of mass m. The body is at rest. At rest, the initial velocity u is equal to 0. When we are applying some force on the body is moving. It gets some displacement s, the final velocity, final velocity v. So try to understand here. Consider a body of mass m which is initially at rest. If some force F is applied on the body, it comes into motion. Now, the work done by the force is equal to gain the kinetic energy of the body. Let us be the displacement. Let S be the displacement. S and V be the, so let us displacement S, V be the final velocity of the body. Try to take all. So this is initial velocity U is equal to 0, final velocity V is equal to V, displacement S is equal to S, acceleration V. So all these terms substitute in V square minus U square is equal to 2AS. So V square as it is, final velocity as it is, initial velocity 0, the 2AS is also same. So A is equal to, we can write V square by 2S. Simply we can take work done, W is equal to F into S. According to Newton's second law, this F is equal to MA. Yes. So substitute this A value here, we get M into V square by 2S into S. SS gets cancelled. We get half mv square. This is the kinetic energy you try to see here. From the equation of motion, V square minus U square is equal to 2AS. Substitute all the values. In this, we get A is equal to V square by 2. A is equal to V square by 2. Coming to here, so A, this is equation 1 or 2. The work done, W is equal to F into S. But according to Newton's second law, F is equal to ma. We substituted here ma into S. Now substituting here, W is equal to MAS, just A, we are substituting, that is V square by 2S into S. SS gets cancelled. Here, SS gets cancelled. We get W is equal to half mv square. Hence, the work done is equal to the kinetic energy of the body because work done on the body sets into motion. Hence, kinetic energy is equal to half mv square. Kinetic energy is equal to half mv square. So, coming to potential energy, you try to give the definition. The energy possessed by a body by virtue of its state or position is called potential energy. So, due to the position or height, due to the state or position, it has some energy that is called potential energy. The energy possessed by a body by virtue of its state or position is called potential energy. Potential energy. So, potential energy formula P dot E is equal to mgh. M is the mass of the body. G is the acceleration due to the gravity. H is the position or state, that is height. Height. This H represents state or position. State or position. So daily life examples you try to see here. Number one, water in a reservoir or water in overhead tank. So water in reservoir or water in overhead tank, the water gets some state or position. So the water is available at some height. And another one is also stretched spring or rubber, a bird on the tree. So try to see here that daily life examples. This is the overhead tank. In this overhead tank, the water has the potential energy. Potential energy. So this is the overhead tank. Coming to here, example. So the bird on the tree. The bird on the tree. To stretched rubber. So you can see action of stretched spring or rubber. So stretched spring or rubber. So this is stretched rubber. You try to understand these are the daily life examples. So potential energy, overhead tank, the water has the potential energy. The bird on the tree, the bird has the potential energy. The stretched rubber, or this is also stretched rubber, has some potential energy. So try to understand these daily life examples. Coming to example, potential energy example. So work done in lifting a body through a height h from the ground is stored in the body in the form of potential energy. It is also known as gravitational potential energy and is given by potential energy is equal to mgrh by r plus h. For example, h is greater than r. You can see here r plus h approximately is equal to capital R. Then this equation we can write potential energy is equal to mg capital R h by r. R gets cancelled. So we get mgh. We get potential energy is equal to mgh. Coming to example 2. Work done in stretched spring. Already we given example here. Stretched spring. Stretched spring related kinetic potential energy. Example, stretching a spring is stored in it the form of elastic potential energy. So this is potential energy is equal to half k x square. This is the stretched spring constant. Stretched spring constant. So kinetic energy, you know very well, the energy possessed by a body by virtue of its motion, that is called kinetic energy. That formula is given by kinetic energy is equal to half mv square. Kinetic energy is equal to half mv square. So coming to expression for potential energy. Expression for potential energy. So let us consider a body of mass on the earth. So this is the body. Let us consider a body of mass m on the ground. If this body is to be lifted certain height. So the body is on the ground. The body is lifted to certain height h. Certain height h. Some work must be done against the gravitational force. Now, the entire work done on the body will be stored in the form of potential energy. So, what I am saying, consider a body of mass on the ground. If this body is to be lifted to certain height, some work must be done against the gravitational force. Now, the entire work done on the body will be stored in the form of potential energy. So, let the body be lifted to a height of h. You try to see here. For lifting, the applied force F is equal to mg. The displacement or height h, we know very well work done F into S. So, what is this? W is equal to F into S. What about F? F is mg, S is h. So, we get mgh. The work done is equal to the potential energy. So, potential energy is equal to mgh, where m is the mass of the body, g is the gravitational acceleration due to the gravity, h is the height. Yes, coming to the work energy theorem, the net work done. What is the statement? Try to understand. The net work done by a force on an object is always equal to the change in its kinetic energy. So, what I am saying, the statement, the work energy principle or work energy theorem, work energy principle or work energy theorem. The net work done by a force on an object is equal to the change in its kinetic energy. So try to see here, the work done by a force on a body is equal to the change in its kinetic energy. That is known as W is equal to half m v2 square minus half m v1 square. You try to see here. So, or we can also give delta k is equal to k2 minus k1 half m v2 square, let k2 final kinetic energy half m v1 square is equal to k1 initial kinetic energy. The change in kinetic energy delta k is equal to k2 minus k1. This is k2 minus k1. Try to see here daily life examples. Try to see here W is equal to the work done. This is taking delta K. So we can see W is equal to delta K. So daily life examples of work energy principle: a car moving in with constant velocity is accelerated. Hence, there is an increase in velocity V1 to V2. So, kinetic energy is increased by the positive work done by the engine. That is, W is equal to half mv2 square minus half mv1 square. Coming to second example, a ball dropped from the height h. Work done by gravity increases the velocity of the ball, and thus kinetic energy increases. That is also known as work energy principle daily life example. Third one, brakes are applied in a motorbike and it comes to rest after a few seconds. Here, work done by the brake is negative. So, with decrease in velocity, kinetic energy decreases. If kinetic energy decreases or increases, that is a change in kinetic energy. The work done is equal to change in kinetic energy, either increase or decrease. That is the work energy principle. The work done by a force on an object is always equal to the change in its kinetic energy, either increase or decrease, either positive or negative. So that is the work energy principle. Work energy principle. So statement and explanation. The work done by a force on a body particle is equal to the change in its kinetic energy. Again, I am telling the net work done by a force on an object is equal to the change in its kinetic energy is called work energy principle. Work energy principle. So try to understand, try to give the proof, you try to understand. Consider a body of mass. Consider a body of mass m. What I am saying, this is the mass. Consider a body of mass m. Let F is the force is acting on the body along the x direction, along the x axis. Then the body moves from position x1 to x2 along x axis, along x axis. What I am saying, consider a body, consider that a body or object of mass m. Let force S F, let force F is acting on the body along the x-axis. Then the body moves from a position x1 to x2 along x-axis. Then the work done, the work done, W is given by, the work done W is given by W is equal to integral x1 to x2 f dx. Let this is equation number 1. Equation number 1. But according to Newton's second law, according to Newton's second law, the force F is equal to ma. Let this is equation number 2. But acceleration, we know very well. A, the rate of change of velocity d by dt of v, rate of change of velocity, that is acceleration. Acceleration. So now substituting Now substituting equation 3 in equation 2. Therefore, F is equal to m into A dV by dt. dV by dt. So what we will get here? F is equal to m dV by dt we get. So for this equation, multiplying with dx, dividing with dx, there is no change. So dx by dt, we get velocity. Dx by dt, the rate of change of displacement is called velocity. So now F is equal to m. This is dx by dt. I am taking here v, remaining dv by dx. This dv, this dx. dv by dx. So mv dv by dx. This is equation number 5. Now substituting equation 5 in equation 1. So try to understand here in previous one. Let us consider a mass. Let us consider a body of mass m. Let force F is applied on the body. The body is moving along x direction or x axis. Then the body moves from a position x1 to x2 along x axis. The work done W is given by W is equal to integral x1 to x2 f dx, that is equation number 1. According to Newton's second law, force F is equal to ma, that is equation number 2. So acceleration we know very well, the rate of change of velocity, rate of change of dv by dt of v, rate of change of velocity, that is acceleration. Now substituting this a is equal to dv by dt in equation, in above equation F is equal to ma. So F is equal to m dv by dt. What about equation 1? This is, you try to see here. So F is equal to m dv by dt, multiplying with dx, dividing with dx. So we get F is equal to mv dv by dx. Now substituting the equation 5 in equation 1. So what is equation 1? W is equal to integral x1 to x2 f dx is the equation 1. So I am substituting the equation 5 in equation 1. In equation 1. So this is W is equal to integral x1 to x2 mv dv by dx. So dx gets cancelled. Dx gets cancelled. So in this term, there is no x. So after some time x1 by t, we get velocity v1. x2 by t, we get velocity v2. So we can change the limits. The body can move the position along x-axis x1 to x2, velocity v1 to v2. So we can change here. So let the velocities of the body increases from v1 to v2. Then the work done W is equal to integral v1 to v2 mv dv. v1 to v2 m1, v1 to v2 mv dv. So W is equal to, you see here, W is equal to, M is the constant, integral V1 to V2, V dV. What is the integration of x dx? X square by 2. So according to this formula, I am taking here, this is M into integration of V square by 2, limits from V1 to V2. So what I am say taking here, W is equal to M into V by 2 limits from V1 to V2. So this is equal to M by 2. I am taking common. Upper limit substituting V2 square minus lower limit V1 square. So W is equal to half M V2 square minus half M V1 square. So this equation is known as work energy principle. Work energy principle. This equation is known as work energy principle. So let final kinetic energy K2 is equal to half m V2 square. Initial kinetic energy K1 is equal to half m V1 square. Then we can write W is equal to K2 minus K1 or W is equal to delta K. This equation is also known as work energy principle. The work done by a force on a body is equal to the change in its kinetic energy is known as work energy theorem. So try to understand here clearly with this. According to the work energy theorem, work done by a force on a particle is always equal to the change in the kinetic energy of the particle. We know that the quantity F dot dr is equal to F dr cos theta is dependent on the work done by force F on the particle during small displacement. Force acts on the particle during the finite displacement. The work done is obtained as W is equal to integral F dot dr is equal to integral F dr cos theta. Let this is equation number one. So consider that a body of mass m, you try to see, again I am explaining, is acted upon by a resultant acceleration force F along the x-axis. Suppose the body moves from a position x1 to x2 along x-axis. Let the velocity of the body increases from v1 to v2. The work done by the force in the displacement is W is equal to integral x1 to x2 f dx, equation number 2. But according to Newton's second law, F is equal to ma. So this is m as it is acceleration dv by dt. So m dv by dt as it is, here you see, multiplying with dx and dividing with dx. So dx by dt, we get velocity. V is equal to dx by dt. You clearly understand here dx by dt. This is velocity. So m v remaining dv by dx. That is equation number 3. By substituting this equation 3 in equation 2, W is equal to work done is equal to integral x1 to x2 mv dv by dx into dx gets cancelled. Then W is equal to the displacement change from x1 to velocity v1, integral v1 to v2 mv dv. So m is the constant. So I'm taking here integral of v square by 2 limits from v1 to v2 as is. So work done W is equal to half mv2 square minus half mv1 square. W is equal to k2 minus k1. Let this is k2. This is delta k. We can write W is equal to delta k, where the quantity half mv square is defined as the kinetic energy of the body. K2 and K1 are the final and initial kinetic energies of the body. If delta K be the change in kinetic energy, delta K is equal to K2 minus K1. Substituting here, we can get W is equal to delta K. The work done, or net work done by a force on an object is always equal to the change in its kinetic energy. That is, W is equal to delta K. Hence, whenever a body is acted upon by a number of forces such as resultant force is not zero. If the resultant force is zero, F resultant into S, so this is zero, we get work done is equal to zero, W is equal to zero. So what I am saying here, whenever a body is acted upon by a number of forces such that resultant force is not zero, then the work done by the resultant force is always equal to the change in the kinetic energy of the body. This is known as work energy theorem. Work energy theorem. So, coming to the summary of this present video lecture, starting with work done. Work done. So, starting with work done. Work is defined as the product of force and displacement. So when a force moves an object over a distance, forced work to be done, two conditions must be met. What are that? There must be an applied force and the object must move in the direction of the force. If you push against a wall with great effort, but it does not move, no work is done in the scientific sense. A simple example is pushing a cart. Your applied force over a certain distance results in work being performed, transferring energy from you to the moving cart. Moving cart. Coming to kinetic energy. So, due to the displacement, due to the displacement by time, we get some velocity. Due to the motion, the body has some energy that is known as simply kinetic energy. Kinetic energy is the energy an object possessed by virtue of its motion. Because of its motion, every moving object from a air from a flying aeroplane to a rolling ball contains kinetic energy. The amount of kinetic energy depends on two factors: the mass of the object and its speed. Faster and heavier objects carry more kinetic energy. For example, a moving truck has far greater kinetic energy than a rolling bicycle because of its greater mass and speed. Kinetic energy is essential in understanding motion, collisions, engines, and even microscopic systems where molecules constantly move, transferring energy through vibrations and impacts. So you can see next one, potential energy. That potential energy formula you know very well, mgh. So due to the state and position, it gets some potential energy. Due to the stretched spring, it stored some energy. So potential energy refers to the energy stored an object due to its position or configuration. A stone placed on the top of a hill has gravitational potential energy because of its height. A compressed spring or a stretched rubber band stores elastic potential energy that can be released later as motion. As motion. Water stored in dams, it is a common example where its potential energy is later converted into kinetic energy to generate electric energy or electricity. Potential energy is crucial because it represents a stored capacity for work that can be transferred into other forms, enabling countless applications in missions and natural processes. Coming to work energy theorem. So we know very well W is equal to half mv2 square minus half mv1 square. So this work energy theorem established the link between force, motion, and energy. It states that the net work done on an object equals the change in its kinetic energy. In other words, if you do work on an object, its motion will change because its energy change or energy changes. For example, when you push a spring, the work you do adds energy, making it moves faster or swing higher. Conversely, if friction does negative work on a moving car, it reduces its kinetic energy. Showing it down, this theorem provides a clear way to calculate and understand energy transformation. So, energy conservation also we can observe here. Total energy in isolated system remains constant, that is the energy related one. So, real world applications you try to see here. Energy concepts are widely seen in daily life and practical engineering. A pendulum swings back and forth because it constantly exchanging potential and kinetic energy. At its highest point, energy is stored as potential, while at the lower point, it is fully kinetic energy. Similarly, roller coasters are built using these principles. The initial climb builds potential energy, which is related or which is released as thrilling motion when it descends, converting into kinetic energy. Engineers use these principles in countless designs from rides to clock mechanisms, ensuring smooth and predictable performance. Energy concepts from the basis of practical engineering solutions. Finally, coming to CSE applications, relevance in gaming and robotics. Even in computer science and engineering, that is CSE, energy concepts play a crucial role in gaming and animation, physics engines, simulations, realistic movements of objects, characters, or vehicles based on kinetic and potential energy principles. For instance, in Angry Birds, energy principles decides how far the bird flies and how it collides. In robotics, and artificial intelligence, energy efficient motion planning ensure robots perform tasks without wasting any power. Additionally, green computing focuses on reducing power consumption in data centers and devices. These examples show that energy concepts are not limited to physics alone, but extend deeply into computing fields. So try to understand here clearly work done. W is equal to F dot S. The product of force and the displacement gives the work done. Due to the motion, due to the velocity, it has some energy, that is the kinetic energy, that is energy of motion. Due to the state or position of the object, it stored some energy, that is potential energy. The work energy theorem, W is equal to half mv2 square minus half mv1 square, that is the net work done by a force on an object is equal to the change in its kinetic energy, that is work energy theorem. So in this we discussed work done, kinetic energy, potential energy, work energy theorem, real world application, how it is applicable for CSC. So we discussed everything. So thank you for interesting for this video. Thank you so much. Thank you one. Thanks again one and all.